Hi everyone, welcome back to Creative Coder's Toolkit. This video, we're going to be building a drawable EQ where you can use your mouse and drag each band on the graph to control EQ bands. It's effectively a 430 band graphic EQ, and we'll get into some very cool applications for this. This video is kind of a direct sequel to my last video, the one where we built a spectrogram. I wanted to make sure that I did that video first so that we would have a visual way of seeing exactly what the drawable EQ is doing to our audio signal. If you would like to have an abstraction of the logarithmic spectrogram from this video, make sure you go watch that one, and it has all of the steps to build it. So the idea of a drawable EQ is that you have an array that you can affect with your mouse, and it controls the amplitude of each block of audio that it corresponds to. Unfortunately, I was not able to find a way to get logarithmic scale to work for it, but it does still work as is. For this application, we are going to need one more new tool called a Hanning window. I went through the Wikipedia article on these, and I'm still not super clear on what the practical application of these are, but from what I can tell, it sounds like typically you apply these windowing algorithms while doing FFT calculations, and it helps smooth out the data. Specifically, it's a symmetrical pattern that you apply to each block of data, and it only allows through the values that overlap. I did find a forum post talking about how the Hanning window was used for an application similar to our drawable EQ, and it sounds like it's simply working as an amplitude envelope, making sure that the audio is never clicking because of jumping from on to off in the middle of a waveform. And that sounds reasonable enough, but I tested this sketch with two different Hanning windows, and the one with more values seemed to be more accurate, which would mean that it does affect more than just amplitude envelopes. So let's start with the Hanning window abstraction. We can make two. We'll make one simple one and one more complex, since our application does appear to be affected by how complex it is. Let's go ahead and open Pure Data here. Get a new window. Okay. Okay, so now that this is built, basically what this is doing, make sure we connect this. When we load this Hanning window abstraction, it load bangs through, and at our current sample rate, which I'm currently at 48 kilohertz, you might be at 44.1, it bangs through. That gets divided by 64, which is the resolution of our Hanning window. We're going to make a higher resolution one after this. That is the frequency that is running through our oscillator. This 0 that also gets banged just tells the oscillator to start at 0. That way we make sure that we're not showing up, somewhere between 0 and 2 pi of our sine wave. And then the multiplication and addition that we're doing basically just get this window to show us the correct phase information of this waveform. And so when we click here, no, still no. How about DSP? Yeah, that'll do it. Always make sure your DSP is on if you're doing audio tasks. So this is what we want our Hanning curve to look like. This one in particular has a resolution of 64 points. For our drawable EQ, we're going to be working at a block size of 1024. So let's build one that is appropriate for that application. And it's going to be roughly the same. But we'll go Hanning 1024. And it is going to have that many save contents and polygon. And again, from 1 to 0. And what we can do is we can actually copy and paste all of these, because the only thing that we're going to change is that value right there, and then the name of the graph. And there we go. Now we have a higher resolution version of our Hanning window. One last change that we do need to make is we need to have a subpatch with our block size increased to 1024. Okay, now we can save this one as, in the abstractions, we'll go, I do Hanning, and then the number for our resolution. For this, I'll go vid Hanning 1024 and save. So those are ready for us to go ahead and move on to our main sketch. All right, so let's open up a new sketch and start laying some stuff out. So we have our array, which we can call gain. You can call it drawable. You can call it whatever you'd like. And we're going to start at 512, and they're going to be points, and we'll save contents. We'll hit OK. Properties, we're going to go from 1 to 0, and we're going to increase the size quite a bit. So this is the graph that we're going to be drawing our EQ on. Let's lay out some of the rest of our logic. Let's say that we have a noise object going through our logic that is controlling the effect that the drawable EQ is having on our audio signal. And then we're going to have it go into a spectrogram so that we can see how it is actually being affected. We are going to need a couple more things here. We have to instantiate our Hanning window. And you can see that we've got that here. And then we need the brains of what we're doing here. So we're going to go PD brains. That opens up a new window here. And we can start building. We've got an inlet. And now this is where we pull from our Hanning window one of the places. And then we're doing a fast Fourier transform. And then here is our gain stage. And what we're going to do is pull the information from our gain array. I'm not 100% sure what exactly these values are doing specifically, but I have heard that they are for normalization, basically taking the values from tab receive and having it fit a more specific range. Go 768. Not sure why they picked that number, but now from out of here, that is what is going to multiply each one of the blocks coming out of this FFT. And then down here, we're going to do the inverse FFT that puts the sound back into the normal time domain. And then we're going to send it through one more Hanning window. Make sure that you declare the block size in this subpatch as well. Send this through there, send that through there, and then finally into your outlet. Okay, there is our brains of what's going on here. And so if we send noise through that and then into our spectrogram, what you can see is that what I draw on here is how the audio is affected. One thing to keep in mind is that while we have a logarithmic spectrogram, we unfortunately have a linear gain array. And so what we're drawing follows just a different mathematical scale. So right in the middle of the graph here, around there, is going to be about 10K, right in here. That is one other thing to fix. Currently, we have this gain array split up evenly for our entire 48 kilohertz. I already made it 1/2 size so that it's only going up to 24 kilohertz, but we don't need anything past 20K. So what we can do is try to figure out how far back we have to draw before it starts giving us frequencies we care about. So right about there. So if we do properties, let's go 450, apply. Okay, got a little bit further to go. 440, apply. 430. That looks about right to me. Okay, so now about halfway through should get us right around 10K. And what we can actually do is leave ourselves some comments to try to make it a little easier to tell kind of where we are. Okay, I got pretty close there. Yeah, that's just about right on. Let's do right around there. Okay, little higher. We'll go right about there. And that is enough for right now, just to give us an idea of kind of what we're drawing and where it goes. An easy way to help kind of reset and reopen this drawable EQ is to go ahead and drop yourself a message block that allows you to set all of the values evenly. So if we look at that, so semicolon, name the array, const for constant, and then 1. This will set every value to 1, let everything through perfectly evenly. And then if we create another one, gain const 0, it'll set everything to 0. Next, we can actually take a listen at what this EQ is doing for us. So we can set a volume object. And an easy DAC. I don't need a lot because this is probably going to be kind of loud. So that's what it sounds like to let everything through. One of my favorite applications for this drawable EQ is to pick single points randomly. And it tends to result in a soundscape that, to me at least, sounds kind of sci-fi or spacey. One nice tool to have is that if you encounter a pattern that you've drawn in your EQ array and you want to be able to save it and then recall it later, what we can do is drop in a save panel and open panel object to be able to save it as a text file and then load it into your array later. So what we'll do is we've got a button here. We'll go save panel first. It's actually not going to be an object. This is going to be a message. And it is going to say, semicolon, name of the array, write, and then $1. And then the other version of this that we're going to use to load a file. So this saves a file. And then to load a file, you do open panel, and then the message that you get from that is semicolon, name of the array, read, and then $1. So what we can do here is make a pattern that we really like, that we want to be able to save. Ooh. Hit the button. Array save .txt and save it. And then if we want to be able to recall it later, you hit the open panel button, find your text file. You can name it whatever. You can keep them organized and keep a lot of different versions of this and hit open. And it loads it right back in. One problem that I really wanted to solve before filming this episode was the fact that this drawable EQ is still in a linear pattern when what we'd really like is a logarithmic pattern to follow the increase in frequency as those frequencies increase. This results in our drawable EQ heavily skewing to high frequencies, like you don't even hit 10K until the midway point. This was one issue I was able to solve for the spectrograph, but no amount of tinkering got me to a usable logarithmic drawable array. If any of you are able to find a way to convert this drawable EQ into a logarithmic frequency graph representation, I would be extremely interested in seeing it and would absolutely make a video follow-up. Please let me know if you have any other questions about things I've made or topics you'd like me to cover. You can leave a comment below or email me at creativecoderstoolkit@gmail.com. Thank you so much for tuning in, and I hope to see you in the next one.